Welcome back, my fellow Americans. I'm your host, President Foosbama, and today we're going to be having another episode of Fun with Foos. Um, Today I'll be doing homework 2, which coincidentally comes after homework 1 that you hopefully watched and now understand. So in homework 1 we learned about budgets, we learned about preferences, and now we're going to combine the two. And awesome, my little scene works. So we are going to combine the two with optimal bundles today. So the idea is, like, if something is really expensive, then I want to weigh that in like how much I value it. And if I get a lot of enjoyment out of something, then I should also weigh that. So we're trying to combine these two facets to find like what normal people would consume on the day-to-day. And how we do that, I think a core piece of the homework today is going to be this magic little formula, MRS equals to MRT. So this is our tangency condition, and what this does is it basically just shortcuts ourselves to get the optimal bundle, or the utility maximizing bundle that these questions are going to be asking for. So just cranking on this, we know how to find the MRS from last time. So we just take the marginal utilities. So I'll do marginal utility of F. And unfortunately, these are going to be a little gross. They're going to look bad. But I swear they're not that bad. I believe, if it works out in my head, that these are going to cancel out pretty nicely. And then we're going to chain rule the inside, and we're doing F. So that's 1/4 F to the negative 3/4. And then the marginal utility of E is going to be the same thing right here, and then times 1/4 E to the negative 3/4. And I know that that's going to cancel. I know that that's going to cancel. So our MRS should just be our F. Nope. That's going to be E on top because we have some negative exponents going on. And then F. And I'm just going to factor out the 3/4 while I'm here to make that pretty simple and easy. So we have an MRS, and we're going to set this equal to our MRT. And our MRT, as always, is just the price of X over the price of Y. So I just made X here my food, so that's going to be 3 over 24. And I think that's just 1 over 8. So let's just write that equals to 1 over 8. And from here, I just want to apply my exponent to both sides. Some simple little algebra going on for you. So let's get, actually I'll write this in terms of, let's get E over F to the 3/4 to make it a little more obvious what I'm doing for y'all that might not be following too closely. So we're going to raise both sides to 4/3. So I raise this one to 4/3, and then this one to 4/3. And I'd probably use a calculator. I've looked at this problem before. So I know that's 1/16 here, but that's probably not an obvious draw. So the 4/3 and 3/4, like, these multiply together, so that cancels. So you just get E over F equals 1 over 16. And then awesomely, we can now cross multiply, and we're going to get 16E is equal to F. And we're almost done. I know these problems can be an absolute bear to go through, but we now plug this back into our original budget equation. So they gave us the 144 for a reason. So we can write out 144, and this is like our budget equation from the first homework, would be 3F plus 24 E, okay? And then we can just plug this in. So I know what F is equal to. So 144 equals 3 times 16e plus 24e. And I think our last little bit is going to be getting this e. So that's 3248 plus 24. Is that 72? We're hoping for a miracle there. I think it's 72. So that is 144 equals 72e. And we divide both sides by 72. So e is equal to 2, baby. And I guess by process of elimination now, since none of them have e equals 2, we can lock in a. If you wanted to find how to get f equals 32, I would just plug that back in right here. So I would say 16 times 2 equals f. And that is, oh my gosh, that is a terrible f. The pen is still warming up, I can assure you. But we're getting somewhere. I think, oh, I was like, what the hell is going on? Okay. With this little fraction bar thing, but I figured out my my hieroglyphics. I was canceling stuff out. So we locked in A. I feel pretty good about that one. A consumer's preferences for good X and Y. Okay. So I think this is just a generic, like Cobb Douglas. So I always want to do MRS equals to MRT. And they give us the implicit, like the interpretation formula. So our change in Y over our change in X. So I can consume 5 units of X for 15 units of Y. So that is 5 over 15. So that's our MRS. Let's just make sure that we know that that was. And this is also going to be our MUX over our MUY. So like this is all the same stuff that we can remember. And our MRT is going to be equal to the price of X, which is 5 over 10. That's interesting. I don't even know why why we necessarily need that piece. So if I were just to cross multiply like bang, bang, because I'm looking at the answer choices here, then I would say 10 marginal utility of X is equal to 5 marginal utility of Y. And then that cancels, that becomes a 2. So marginal utility of X is equal to marginal utility of Y. And that does line up. Yeah, I have no idea why she, I guess this piece is just like a red herring. I think all you need, since she just gave it in generic terms of marginal utility, I think all you just needs the MRT to solve that problem. But that one was a little quickie. Okay, we have $500. The price of this. Okay, I remember this. This one's a little tricky guy. So I'm going to hit you with a little bit of plot armor and hear me out. I've seen this problem. So I think it is fair to say that we always want to start with MRS equals to MRT. That's just like always going to be our shortcut for everything. So marginal utility of X, that's going to be like 2X over 2Y. And then we're going to cancel. So our MRS is just X over Y, and our MRT is equal to 25 over 50. And we're going to get 50X is equal to 25Y. And we can just like cancel that out. So 2X equals Y. So nothing crazy yet. This is pretty standard stuff. And then you would go back and you would plug that into this piece, our budget equation. So we get 500 equals, how am I going to plug that in? 25x. Sorry, I'm brain farting. 25x plus 50 times 2x, because I know what y is. That's the point, is that we're trying to isolate for one variable. So then I get 500 equals 125x. And if I divided that over, then I would get x equals 4. So I think this is what they want you to get. This is a tricky guy. So one core piece that MSA will typically try to preach and is sometimes kind of valuable, most of the time is not very valuable, but in this very niche instance is incredibly valuable, is if we took DMRS dx of this thing, DMRS dx and DMRS dy, then we would figure out, this is our MRS, so we have a positive derivative up here and a negative derivative down here. I believe it's going to be negative x over like y squared. Is that maybe possibly correct? I know it's negative by using our arrow math from what I taught last time. So what this tells me is that as x gets greater, our slope is also getting greater. So we have a little concave curve. In one lesson about concave curves is that they always have a corner solution. And why that's the case is because if I were setting it up, so like on a corner solution, you're always trying to find the tangency. And the tangency is going to be right in the middle, right there. But I can always move to a higher indifference curve. Like this isn't the best one. The tangency isn't actually the best case. So if I move to a higher indifference curve, let's say this guy, then I could intercept right there and I would still be on our original budget line. So like we're good there, and I'm on a higher indifference curve, so I'm getting more utility. So I think the upshot of what I'm trying to convey to you is most of the time I personally do not check for the curvature. And if you had just stopped at x equals 4 and locked that in as your answer, then you would have gotten burnt and it would have been bad. So MSA always preaches like check the curvature and make a graph for like literally every problem ever. And technically that's proper protocol. But in this specific problem, that was a requirement. You did need to have that to figure out it was a concave curve. And then once you know that it's a corner solution, we're just between A and F. And obviously 20 squared is bigger than 10 squared. Like this is for option F would be 20 squared. And option A was for, this is option A plus 10 squared. And this is option F. So obviously 20 squared is bigger than 10 squared, and that is why our answer is F. But that's definitely like probably one of the trickiest ones on the homework and is meant to try to get you to pick that D answer. And that's messed up. I don't know who made that problem, but they're tricky. They're tricky. Okay, so a consumer uses all their stuff. So the marginal utility per dollar, I think by definition, this phrase right here, I think is what the bang per buck is. And just a review, our bang per buck is the marginal utility of something over the price of the other thing. Or no, the price of the same thing. Okay. And is saying that the bang per buck spent on food is greater than the marginal the bang per buck spent on gasoline. So just like from a 2-second glance, I will tell you that that is false. And how I made that intuition is the tangency to get to a higher indifference curve is pretty much always going to be in the middle of the line. And you can kind of just commit that to memory that like basically the tangency is always going to be in the midpoint of this line. That's just most of the time how it rolls on on these bang per buck problems. And what's valuable here is we can just say that I bought, starting from this point, I bought less food and I bought more gasoline. So I would know that the marginal utility per dollar spent on food is less than the marginal utility per dollar spent on gasoline. The bang per buck is better for gasoline, so that's why I'm buying more of it. So that is opposite. This would be less than the marginal unit per dollar. So yeah, hopefully, I don't know if I gave that question the whole justice it deserves. But I think that's like immediately where I would go with the problem. And I would just not think too deeply and assume that I will get a stronger theoretical understanding of the problem throughout like recitations and doing more of these stuff. Oh, let's go. We got some Pokemon cards. I wonder if we're going to pull the foiled Charizard. Okay. The price of a pack of Pokemon cards is $5 and blah, 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 blah. We got normal assumptions and we are at 10 packs of Pokemon cards and 5 packs of baseball cards. So here it also gives us the 2 Pokemon packs for 3 baseball cards. So that means that we have perfect substitutes that are change in y over our change in x. Let's assume Pokemon cards are x, I'll just say. So for 2 packs of Pokemon cards, we have 3 packs of baseball cards. And this is our marginal utility of x over our marginal utility of y. And we have our MRT, of course, which is 5 for Pokemon cards, price of x over the price of y. So we now have a marginal utility of x. I'm going to try, so we got 3 over 5. So this is for our x, our Pokemon cards. And then for y, we have our marginal utility of y, which is 2. And the price of y, which is 3. And I believe 2/3 is 0.66, and this is 0.6. So this is going to be greater. So I am going to want to invest in, and let's make sure, so 1, 2, 3, 4, 5, that the answer is B, that we are going to buy more baseball cards and less Pokemon cards. So yeah, that lines up. That since the bang per buck, we always want to buy more of the higher bang per buck. So in this case, the Y was our baseball cards, the X was our Pokemon cards, and 2/3 is greater than 3/5. So we're going to buy more of Y. And that is why we're going to shift. Okay. For the next one, we got some Kit Kats and yogurt. Kind of a weird combination, but some perfect substitute. Okay, Kit Kats and yogurt are definitely not substitutes in my book, but that's okay. We're always willing to trade 7 Kit Kats for 3 yogurts. So to start this problem, I note that we have perfect substitutes and we are given that the change in y over the change in k, that's just our MRS formula, equals the MRS, and that is equal to 3 over 7, because we got 3 yogurts for 7 Kit Kats. So here's our magic 3/7 that we can get rid of the rest of these guys. And probably what I would do from here is I would just write like this is the MRT, and it might help us explain what we're looking at. And this is our MRS. So whenever we see 3/7, just think that's our MRS. And I will be honest, I would have a very tough time with this problem. It is quite conceptual and quite tough. But luckily, I have seen the answer key. I have the wisdom bestowed upon me. Where I would go with this is, let's imagine that we just have an arbitrary MRT. And let's say that this is, let's label our axes first, and y. So if I made this MRT arbitrarily 3/7, let's say that our MRT is equal to 3/7. Then if I had, maybe I'll point to it too, to make sure that we know this is our MRT. So our MRS are also going to be straight lines because we have perfect substitutes. That this is just like a fixed slope. And if I made it less steep, if our MRT was less steep than our MRS, then that would mean that I'm going to draw MRSs that are more steep. And what's magical about this is I can keep going with these MRSs, these indifference curves, until I hit the highest one. The highest meaning like is the farthest away from the origin. So when we have an MRS that is greater than, it is more steep than our MRT, our original budget line, then I am only going to buy Kit Kats because this was our farthest point. And we can just reverse the logic. So if I were to do it again, and I made this budget line, then if I made a bunch of indifference curves that are kind of arbitrarily less steep than this 3/7 threshold, then I would go like that. And sorry, they should be straight lines. But you would also get to a corner solution of only consuming y. And it's going to be at the end of the budget line, obviously, because we want to expend all of our money. So I am hitting you with a little bit of like, yeah, bro, I just explained something that I personally think that this is the hardest like thing to conceptualize on the homework. And probably the main takeaway is the converting the language. I think when it's in this form, like PK over PY, it's really hard to understand like what they would be asking for. But if you just kind of view it as a matter of this is the MRT, this is the MRS, and we're literally just asking about the bang per buck stuff that we've been asking for the other questions on this homework, then it becomes a little more tangible and a little more possible for the average Joe. For the next problem, we have more perfect substitutes. Yep. So we are given a budget constraint and we're looking for a utility function. So the way I like to deal with perfect complements and perfect substitutes when I'm trying to rebuild a utility function, one trick you can do is you literally just do a little flippy floppy. So if 5 is attached to t, then just like scrap that out and put a 2 there. And 2 was associated with coffee, so now I'm going to put a 5 there. And we're going to get 5C plus 2T, because that's just kind of how it works. If you want a more intuitive explanation on that, basically, and I'll just erase that. So we know that 2 cups of coffee are worth 5 cups of tea. So like what that means to me is that a cup of coffee is more valuable than a cup of tea. And that might be a little confusing at first, but just like really think about that. Like if 2 cups of coffee are worth 5 cups of tea, a coffee is more valuable. So when I plug that into the utility function over here, then the coefficient on coffee, like coffee is giving me 5 utils per coffee. Like if I plus 1 the C here, then I would get 5 utils. Whereas this one, I only get 2. So that indicates to me that, since it has a smaller coefficient, it gives me less utility, and thus, since we established that coffee was more valuable, that we are going to be on this 5C plus 2T timeline. So that's going to get rid of B and D. And her optimal bundle, so we only have corner solutions because we're on a perfect substitute. And I think it would just be, you can really just plug it in at that point. So does 12 cups of tea, that would be a utility equals, I'll just write out the whole thing, plus 2 times 12, which equals 24. Or would I rather have utility equals 5 times 3 plus 0 equals 15. So obviously, since 24 is bigger than 15, we are going to go with that one, and we're going to get C. For number 8, I think we're doing pretty similar stuff, but this time we have perfect complement, so it's going to look a little different. But you can use the same flippy-floppy strategy. Flippy-floppy normally goes pretty well, but sometimes I'll gaslight myself. Like, if you don't pick up on the intuitive understanding of what it means, you'll be like, do I flippy-floppy? There will be some weird example on the exam, and you're like, whoa, that looks really weird, bro. So in order to not land yourself in some hot water, the intuitive understanding is pretty good. So in this case, the 2 teaspoons of sugar for 1/3 cup of coffee. So it's the same as last time. Our cup of coffee is worth way more. If like 1/3 of a coffee is worth 2 teaspoons of sugar, then coffee is super good. So that would tell me that the coefficient on coffee, so like when I plug in 1 coffee here, the coefficient compared to S is going to be way bigger. And that makes sense. Like the utility function is literally like is telling me the utils based on when I plug in a certain bundle. So I know that if the coefficient is supposed to be bigger, then at a 6 to 1 ratio, then it's definitely not B, definitely not D. However, I do not know. It could be this one because it's the same ratio. They just divided it by 2. So now we're going to have to look at the budget. And I've done a little bit of cheating. I've also done this problem. So what I would note is compared to A, C just like buys more. And what I did was, I know we spend our whole $20. That $20 will be spent, and the price of a teaspoon of sugar, so that was 0.25, so that was divided by 4. Sorry, I have to bless myself. Maybe Jesus will come down from the heavens. So that cost $12 because each one was 25 cents, and a cup of coffee is $1, so this is $8. So when you add those together, you get 20 bucks spent. And if you do that with this one, you get 6 plus, what is that? 36 divided by 4 is 9. There you go. That's the math is mathin', baby. So that's 15 bucks. And spending 15 bucks is obviously going to get you less utility at the same like trade-off compared to 20 bucks. So the optimal bundle is going to be C. And we're almost to the end of the MCQs. The MCQs are normally my favorite. Long forms are always they're drawn out. She'll throw in some stupid example that makes you want to die. And it's a time to be alive. But okay, so we're given kind of selective information here. We're given some stuff, but not all the stuff. And once again, I think we're just going to default to MRS equals to MRT. And this MRS might be a little bit ugly. So my marginal utility of X is going to be 2/3 X to the negative 1/3 Y to the 1/3. Oh, it's not going to be too ugly. And then we get our MUY of 1/3 X to the 2/3 Y to the negative 2/3. And we can move that guy up. So that guy comes down for negative exponents. The thirds are going to cancel. So we get 2. This guy goes down. This guy goes up. So 2y over, let's get a little tail on that guy, 2y over x. That is our MRS, which is equal to our MRT. And our MRT, we don't know the price of x, so I'm going to leave that as a generic price of x. But we are given that our price of y is 4. Yippee! And with a little cross multiplication, we got 8y equals the price of x. Price of x times x. Okay, we got to make sure to keep our x. And we are told that we are purchasing 6 units of x. So we are told that 8y is equal to 6 price of x. And my final step would be to get, we got 72 bones in the tank. We got our price of x times x. So price of x was, we don't know, but we do know the amount of x is 6. Plus, we know the price of y is 4, and this is times y. What I would do personally is I would divide both of these by 2, because I want to match this 4y over here. So that would get me 4y is equal to 3 price of x. And what I can then do is I can say 72 is equal to 6 price of x plus 3 price of x to get a total of 72 equals 9 price of x. And if we just do a little division on both sides, we'll get price of x is equal to 8. This is a nifty little trick. I think that one is definitely not an obvious one. One thing that we'll note that's a pretty recurring theme is when you want to solve for one thing. So like the question asked me for what the price of x was, then I want to plug in y. Like I want to isolate y so that we just get something in terms of price of x. So that's why I tried to match up the y that I saw from here to the y in our equation. So I could just like immediately plug in and get everything in terms of price of X. So a little bit of nifty math tricks, but nothing like too crazy, I would say. I think it's still the same steps of just like MRT equals MRS and just kind of scrapping it out with more generic stuff. Like they don't give you physical numbers, but they give you some variables. And I think this one is like really conceptual, that like I'm just gonna kind of hand wave this this problem, that you should know that for Cobb-Douglas, a corner solution is never possible, because if I plugged in 0 for either of these, then the whole thing becomes 0 because they're multiplied together. So like if I did 0 times like whatever y is, it could be 100. So like 0 times 100 to the 1/3, like that's still 0. So corner solutions for Cobb-Douglas are just never possible. For these, I'm gonna hit you with like, we just talked about perfect substitutes and how like we always get corner solutions there. So that's not an issue. We have like some quasi-linear stuff that like you generally have to check. There's no like straightforward answer. I believe I'm going to go to the key. This is another quasi-linear for like generally quasi-linear stuff. When you have like this mismatch of like some exponents and some non-exponents, you just always got to check it. You always got to assume that it might be something. And for the min function, the perfect complements, remember, oh my gosh, that is that is a sight to behold, that we got something like that. And it'd be really hard to like, if that is my budget line, like my like to make a corner solution, I'd have to go like that, which like doesn't make sense, because if I paired, like this would be asking me to pair like my amount of good X with like a good Y, but one of them is 0. So like that inherently defies. Perfect complements are like, I need both of them at the same time. So like I can't have one of them be 0. So it is just like physically impossible for this case to be true. What they are always going to look like is like some generic form of like it's going to intercept at some point on your budget line. And that's just how perfect complements work. So pretty conceptual question here. I think you could like drill these into your brain that like, are corner solutions going to be possible, yes or no? It's kind of a common like exam problem that she throws onto stuff, of like, could it be a corner solution? And that's how I would tackle it. So I really don't want to write out all of the Lagrangian garbage that's going on here. So I'll do my best to draw your attention to the most important pieces of how to set up a Lagrangian equation if you feel unconfident with that. So this first problem asks us just to use the Lagrangian method to calculate the bundle. So the first step of that is, this is our utility function right here. So what I would do is, I found the utility function in the problem. Boom, plug that in. And it's always going to be utility function plus lambda. And then you're going to take your total income, and then you're going to, or actually, let's use generic things. We're going to plug in our entire income, and then minus the price of X times X minus our price of Y times Y. And this is just always the case. You can commit this step to memory. The Lagrangian equation is never going to change. And why this is special is because when you take your income and you spend all of your money on either good X or good Y, we are guaranteed that this entire parenthesis term is going to zero out. So it's going to be like parentheses 0 at some point because we're spending all of our money. And why that's awesome is because we're multiplying our lambda by 0. Like we're effectively adding nothing to this. All we're doing is just making it easier so that we can do math on it and we can expand to get this optimal bundle. But like we're essentially doing nothing to break math. We're not like changing anything in any way. We just have our utility function. And what you do from this step is, I'll try to clean up a little. So once you have your Lagrangian equation written out, we always just take these first order equations, and this is just the partial derivative. So, for this example, you would just like knock off the f, the 5v would disappear, and you're always going to get the corresponding piece from your budget. So like the lambda, it's going to distribute in. So you have minus 5f lambda, and then since we're deriving with f, the f drops off, and you'd get minus 5 lambda. And you do that for this one and this one, and your first order condition is always going to be just this piece that you already did, the income budget equation set to 0. You can just autopilot that every time. It's never going to change. It's a universal constant, age-old tale, some might say, or at least before my time. And the first order condition, in order to satisfy that you have is a first order condition, is you have to set equal to 0. That's like what makes it a first order condition. Because if you just took the derivative of this thingy, that would just be like some partial derivative floating in air. But when you set equal to 0, that's what they mean by first order condition. And from here, what I always do is I scooch these guys over to the other side, and I just make one big fraction bar. So when we scooch this stuff over the other side, we got v over f plus 5 and 5 lambda over 5 lambda. And why that's awesome is because the lambdas are always just going to cancel out. And I think how I would write this is something like that. I like making the same steps every time. I don't like channeling. I don't want to have to think. Thinking is bad. So you just cross multiply. You get v equals 5 plus f because we just cross multiply by 1. And the last step is going to be you plug this little guy into the budget equation from earlier. And in this case, we just want to follow the algebra down. We got f equals 1.5. And then you just plug that in back up here. So v equals f plus 5, 1.5 plus 5, and you get a final of 6.5. And I know you're like, Robert, do we have to do this ever? Yeah, it's miserable, bro. I know. The Lagrangian sucks, and luckily for you, in part 2, we know it sucks. So now you're not required to use the Lagrangian. You can go back to your little MRS equals to MRT ways and be a little smart ass about it. Then you know how to find the optimal bundle without the Lagrangian. So in this case, she just set MRS equal to MRT. Our MRS is actually, we found it from earlier. So when you take the partial derivatives of your Lagrangian, this also finds your marginal utility. So this was the marginal utility of f, was v. So we take the MRS, we take equal to MRT, and in this specific problem, I believe they changed up our MRT, and that's why it's an interesting problem. So they swapped up our MRT, And interestingly, we solved that through, hopefully by now you guys have a solid grasp on how to solve MRS equals to MRT. And you solve that through, and we get -1/2. So this is the key indicator. Negative is always a corner. And what I'm going to do is I just scooch to the next best thing. So like if my tangency was at -1/2, then the best I can do is just go to f equals 0. Like I can't get -1/2, but I can do the next best thing, which is find none of f. And that is going to get us our bundle for part 1b. And I believe, yes, the next part is asking us, how does our MRS compare to our MRT now? So we got a bundle last time. So like our MRS stayed the same. It was just V over F plus 5. And I can literally just plug in what I got. So like similar how we did plugging in bundles on homework 1, we can just plug in this bundle and we get 8 over 0 plus 5, which is 8 over 5. So that's our MRS. And our MRT is, in this new problem, they changed it up to 10. So that's why it's 10 over 5, which is 2. And we obviously know that 2 is greater than 8 over 5 at point B. And that is all it's asking us. So when it's asking us this word compare, that signals to me that she wants to see you like quantitatively say like which one is greater than or less than. I think that would be the major piece of getting points on that. And for this one, how I would start this graph is I would first draw the budget lines. So we know that this first budget line for part A was going to be like we could first afford 8 fruit and 8 vegetables. And then we went down. So like since our MRT got steeper because it went from $5 to $10, like our MRT went from 1 to 2, then I can afford less fruit. So like before when fruit was $5, I could afford 8 of them, and now I can only afford 4 of them because now they're $10. And this intercept does not change because like vegetables, they're chilling. And we can plug in both of our bundles. So like from part A, we got whatever 1.5 and 6.5. So you just take your little dots and get that cooking. And now that we have part A and part B plotted, the last piece is to get these indifference curves on the graph. And I'm a little disappointed. Whoever was making this key was lazy. I think the core revelation that you need to know is that when you plug in the 6.5 at 1.5 and 6.5 into the utility function. So if I were to do like f, so 1 point, oh my gosh, that is terrible. If I do 1.5 times 6.5 and plus 5 times 6.5, and I were to do that for the other one, so I think it was like 0 times what, 8 plus what is it, 8, 5 times 8. So what that is going to get you, I'll get a little quick calculator going, is 5 times 6.5 plus 6.5 times 1.5. So 9, Oh, shoot. Okay. This is 9.75. I had it and then I completely sploofed it. This was 32.5 and this I know is 40. So if I were to add 9.75 onto that, this is equal to 42.25. So why did I do all this, you might be wondering? To show that this was from part A and this was from part B. So in part B, our utility was 40. And in part A, our utility was 42.25. And why this is important is because that indicates to me that since part A gets more utility, that's going to be on this higher indifference curve. So like a really important piece to this graph is that this indifference curve is going to be on a higher indifference curve. And we want to remember that we had a tangency on part A. So like when we solved for it, this came out and just barely touched. It just touches at 1 point. However, our tangency condition didn't work for part B. So it's not going to just be touching, it's going to be going through part B. And she specifies that like her MRS is less than 2, so like our MRS is less steep than this budget line at part B. And it's definitely hard to draw. I think even on the key, she like did a little bit of flubbing here on like, that's definitely too like discontinuous. She like realized that she needs something less steep, and then she went back to trying to match part A. So I think the takeaway there is like your graph doesn't need to be perfect, but like make sure that your A is above and make sure that B like cuts through and is not tangent to. And I think that is what would get you full points on that. And this question also kind of sucks. That I really don't want to do this problem. Lagrangians always just make me sad. But I'll just like really quickly go through the same steps. Same thing. We took our utility function plus lambda minus income minus price of x times x, blah, blah, blah. So same setup, same derivatives. This gets you like the marginal utility. We scooch over the two lambdas. You put a giant fraction bar over everything. You get some ratio of the two variables in terms of each other. And then you take whatever that spat out and then you plug it into here and you find numerical values for both of them. Is like the best way I can explain it. And I know that's gonna suck if you like are really lost on if like doing the math is tough, then like me speed running through that explanation is probably a disaster for you. But like really I'm trying my best. Like if you take each thing step by step really slowly, I don't think that like any of the skills in the Lagrangian part are any different from what we've been doing for the class already. One interesting note I will say is sometimes I believe you may not know. Okay, I think you always get something in terms of this, in one variable in terms of the other. But if you didn't, like let's say you got like E equals 1 here because, I don't know, somehow your lambda is magically matched up, or, oh no, I think you can, like if your marginal utility doesn't have S in it, or like something cancels out, then you might just be given like a static, you might already have a piece of your bundle here, and then you just plug in and hopefully it works. The next step is always plug this thing into your third first order condition, which is just your budget equation. So sorry if this is not completely awesome for you. like in this problem, I think the important piece is that the MRT changed. So like when it says we received $2 from the government lowering the price, that would be factored into right up here with our income statement. Now suppose instead that the government gives ASHRAE a lump sum. So the difference here is this was for part A. Part A changed this price, and part B is changing how much income we have total. And I would bet that that's going to change like how our bundle worked out. Yes, and it does. So luckily we did another loosening of, you can just MRS equals to MRT. They solved for that. So they got E over S to the 1/2. They probably squared both sides. Blah, 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 blah. Plug it into your income. Like it's all the same. You solve for something, you plug it into the budget. That solves for one of the variables, and then you plug the variable you just solved for back into like whatever you had up here, and I can assure you it'll work out. The best way I can explain it is just like do problems yourself, and you'll pick up on the patterns. The patterns are like pretty obvious, and you'll get into the groove. And everyone's really slow at first. Don't be ashamed. But you'll pick up the pace, and you'll start to. You'll never enjoy them unless you're just a masochistic freak. Although I do know a few of those people in the econ department. But hopefully it will become easier over time for you. And mathematically determine and justify which bundle we prefer. So this is what I just told you that I just did in my like from up here on number 1. This is when I calculated the utility for the bundle. That's what it's asking for, is like literally for us to find which bundle is preferred. So she goes through that work, just plugs in whatever you got from the previous ones, and obviously 120 is smaller than 135, so I would want bundle B. And one last problem on the graph, clearly illustrate the bundles. Okay, it's another graphing problem. And it's going to be a similar thing on, it's kind of a little tough to draw though. The MRT was steeper on the lump sum, which would make sense because we don't get that subsidy that made the price cheaper. So like the price getting cheaper changes our MRT. The lump sum does expand out. So like a change in income, if I change this income, that's going to make like literally the same line. It's either going to shift, inward or outward. So like if this was my thing, then it would either go like this way or this way. But since the prices don't change, like it's still going to be the same slope. But in this case, on our subsidy, the MRT did change. So this is like a price, I guess let's just say it's the price in X. And we went from, like if the price in X changes, you're going to go like a steeper or less steep relationship. And that's kind of like a general rule of thumb that's how changes in income and changes in prices look on these graphs. So not going too much into detail on this one. If you followed the Lagrangian MRS equal MRT stuff, then you would get these bundles. And just note that once again, the lump sum one should be on a higher indifference curve because that's what we found in 2C. And also, I don't think I mentioned this yet, but the indifference curves can never be crossing. If you ever find an indifference curve or like this guy went through that guy, then that's a disaster. You know that you're a complete failure and should probably quit in life. I'm going to keep it a buck. No, it's not that serious, but just remember that these guys are never crossing. And with that, we're at the bottom of the document. I think we've fully finished the homework. That was really long, and I'm realizing that after doing the Lagrangian, I feel really sad and my voice is starting to kick out. So I'll try to just run through these guys as quickly as possible. The bang per buck help sheet, I think, would have been useful. It kind of tells us, like, definition, what the tangency condition was and what a bang per buck is. It is a little useful that it kind of tells you, like, the wording on this marginal utility stuff. So, like, for example, when we had a case, that's the answer key. Okay, like on number 5, if you were like, how do I tell which one I would want to buy more of, then this help sheet would be super awesome for you. That like you don't know the direction of which MRS equals to MRT works out. Personally, I always just default to like, you always just buy the thing with the bigger bang per buck, and like that just means that you're shifting toward that. But I'll leave that in your court as to how you'd like to figure that out in your head. But the bang per buck help sheet can be somewhat useful if we're still like trying to figure out what bang per buck actually is. This corner solution help sheet I thought was pretty good. This question I think comes from the help sheet, like it's kind of ripped from it. And also this the concave question, wherever we had that. So number 3 is also kind of explains to you like why a concave curve is always a corner solution. And what is this stuff? Oh, this is explaining, like, hopefully in the poll in class you figured out what a corner solution was authentically. That's one of my favorite polls. But if you didn't, then this is just explaining that the tangency condition sometimes will get you something outside of your bounds, in which case the best option we got is just to scooch to the next best thing in our bounds, which is a corner solution. And our last one for our last help sheet for this module is about perfect substitutes and perfect complements. This stuff is a little gross. I guess for perfect substitutes, it's a straight line for your indifference curves. So it's kind of interesting to note that they could be overlapping and you could just have infinite solutions. Or you have a corner solution. Typically it's going to be a corner solution, but I guess you could have infinite solutions. And this stuff is going to be telling you that reminder that we can't have a corner solution, and generally just like how to graph this stuff. It's a little gross in terms of I'd be sketched out. I would not try to memorize all of this math. I think that what we did on the homework problems is pretty sufficient understanding of what you would want for an exam. But it is here if, like, what I love about help sheets is that they are very condensed resources. So if you just want to take like a little gander and see what's going on, then I think it's like a good preview material. But like this help sheet, I would not gander too long at, or else you're going to become really sad. And instead, I would just try to focus on these homework problems and just kind of intuit like what these look like on graphs and how I would do them. I also like the little flippy floppy. The little flippy floppy rule is good for perfect complements and perfect substitutes. You'll get a lot of use out of that, that tip and trick. But with that, I think we're done. It's been a, holy moly, it is 12:33 a.m. in the Davis Library. Hopefully you guys enjoyed another successful episode. I know that motivation it's rough. It is rough to keep going. It can feel like this class is way out of your depth. But I can assure you, you are a trooper, particularly if you're still here after 2 hours of watching some idiot work through these problems for you. You are definitely able to get a good grade in ECON410. But with that, I thank you guys so much for watching, and I'll see you for the next homework number 3, baby. See ya.